Okay, so now let's talk about how we actually solve this. This is kind of interesting. So the neural architecture, so the learning problem is they say, hey, we want to compute this conditional probability. I'll build this a little bit. So this lambda, this is the truth value for ground atom alpha. Alpha is one of your target atoms. So I'm looking at the probability of this value conditioned on that value being for alpha, the weights, the program template, the language, and the base set of facts. Okay. So no big surprise there. And there's what those all mean. And such that the following loss function is minimized. And this is a cross entropy loss over the pairs of atom and value of that atom in the ground truth. So notice we consider this value to be either 0 or 1 in the ground truth because we know the right answer, but in actuality it's going to be fuzzy, which is why we have the probability. So they like to say, hey, this is a one big conditional probability produced by this neural net, and we're solving for it, based using gradient descent. Okay, so they have these high-level constructs, and they say, hey, there's these series of these functions, and this looks really tough to follow, but it's actually not that give us that probability. And what's going on with two of the functions are really just translating symbols to vectors, and that's it. So this is just saying, it's just giving you the value for that ground atom in vector X. This is taking a set of facts, and it's giving you a vector where for everything in the set of facts, the associated position is 1, and if it's not in the set of facts, it's 0. It's like pretty simple. And we also have this thing that generates the templates. Again, this is just iter tools in Python or something like that. It's just enumerating out all the clauses for a given template. So when you look at all of this, really it comes down to F infer is the main thing that does the work. F infer is the actual neural network. And so you can kind of see in this flow here, what's going on is they have the axioms, which is the base knowledge set B, is just converting that into a vector, and then it has language and the templates, generates all the clauses. There's the clauses, the weights, initialized at whatever, starting point you have, infer. This is, running gradient descent on the neural infrastructure. Here's your conclusion. Now you compare it with your target value. Cross entropy loss is what I showed you before. And that's kind of the flow of everything. So not too hard. I mean, in terms of big picture, it's really, really quite standard deep learning stuff we're looking at. So let's look at how this infer thing takes place. So we have this G, J, K, P. So J, K is a pair, P is a predicate. And what this is doing is for these two Fs, it's taking the maximum of the two. And you can think of these two Fs. So you're taking that A vector. So the A, you could think of that as a vector representation of a set of ground atoms. Okay? What these two Fs are doing is for two of those clauses, one from the first template, another from the second template, because we're going to pick one per template. What one step of the inference process will conclude. Okay? So you can think of this as G, J, K of P. This is like applying the fixed point operator for rules J and K together on A, and it gives you vector representation X. All right? Now note vector representation X is only going to have non-zero values for things concluded by those rules. It's going to have 0 for everything else. That's okay, because that's all this little piece does. A is what they use. This is where all the weights, well, not weights forever, but this is where all the values for each of the atoms is stored. The subscript is based on the number of inference steps. So the very first inference step, we start with all of the ground atoms in B get a 1, everything else gets a 0. No rules have been applied. All right, so this is kind of where it started, and this is what happens when, for 2 rules, the output that's applied. Okay, so notice that JK pair. So with that in mind, for a given JK pair at inference step T, C PJKT is just the application of G on A at time, or at inference step T. Okay? And the reason we have all these subscripts is, remember, actually at the beginning, we have a limited number of inference steps. So the whole neural infrastructure is replicated T times, which is why you have that. So okay, how do we then update this across all JK pairs? So what we do is we have the result of the inference step, which is just taking a max. So notice, up until this point, I've not introduced any parameters. Okay? And we are picking a pair of those templates, or rules rather. One from one template, one from the second. Here we're looking at summing over all pairs, and we have that C vector from there. And now here is where we assign the weights. Okay? So B of T, BTP, is giving you the resultant inference of all the rules. And the intuition here is you could think at every inference step, I'm applying all the rules, but I'm applying them probabilistically, or I'm applying all pairs of rules probabilistically. This is the probability at which I apply this one rule. I add them together, and the expected value is what updates in that B. Okay? So remember from before, when we had that G thing, or this G thing here, the result of the G thing after input A is only going to change the atoms and the rule heads from these 2 rules, J and K. So for all these C's that I'm summing up here, except for conclusions of those rule heads, everything else will be 0. Okay? So I still have to do one more step. I have to add back in everything else. So that's where they come up with this F amalgamate. And notice this is the last step of it. Or last piece of an inference step, because now I'm iterating my inference step by 1. So I'm amalgamating A of T with the sum over, this is if I have more than one target predicate now, over all the B's, which was the result from the last slide for each target predicate. If there's only one, it's just the B from last slide. Okay. So amalgamate, originally they wanted to do max. And they actually had an idea that, hey, if we use max, we can have arbitrary number of rules taken at each step. It turned out that in practice that didn't work. They had an issue with rules overwriting each other. And so they went with a probabilistic sum, which is why, if you remember from a little bit ago, we're looking at pairs of rules and we're taking the max from the pair. So in this way, we still get multiple rules, but they couldn't figure out a way to get around having pairs. There's been, I think, like 3-4 direct follow-on papers to this. None of them, could get around this problem. Yeah.
So, repeat again, like why they use the max in the first case. Why is it necessary to use that for the pairs?
So it's not apparent from this mathematics, but what you could do is, so what you could do here is you could have for each, instead of having one variable for each pair of rules, you could just have one variable for each rule. So instead of having, I'll just say n, but that symbol is used for something else later. But instead of having n squared, you would have n rules, and then you could take max. You would have a bunch of things here, and then you could take the max over all of them, maximum value for that position. But they said when they did their implementation, that wouldn't give good results.
So if it's like an inference step, like that there are two classes and then they give some inferences and we are taking a max, then it's like more like an union over the voids each of the clauses gives.
You can think of it as a rule that is a disjunction over the body of both rules. That's one way to figure it. Max is commonly used in fuzzy logic for disjunction.
So it could just as well be two separate rules.
So they are two separate rules, but what we're doing is we're picking a pair of rules. And so that's why they're doing it by pairs. So they have, if you remember the way they create that vector is by JK pairs. Other questions on this? Yeah.
Can you explain a little bit on summing up the V?
Oh, this is if you have more than one target predicate. So if you only have one, then you use two. And the reason why is because you're going to have a different set of rules for each target predicate, and all other positions in that vector will be 0. That's all. So you just add them together and all right, so one more thing is, so we had that function f that I just said, hey, the rule gives the result that goes into the vector, but I never said how it was done. The fuzzy logic behaves the same way as in logical tensor networks, and the authors explored, since the bodies of all rules are conjunctions, they just explored a couple different things. They found that the product T-norm worked the best, which is interesting because that's also what worked the best with logical tensor networks. They said that basically it had the gradients flowed more evenly when you use product as opposed to using the other things. And that makes some intuitive sense.